Hello everyone. In this video, we are going to study schedules from a recovery perspective, right? So the point to be noted is that even though the recovery manager is a completely different module from the concurrency control manager, but they are not designed completely independently of each other. They go hand in hand, and it is the duty of the concurrency control manager to help to create schedules, to allow schedules which are not only conflict equivalent to a serial schedule and all that, but they are also easy to recover. So for example, you may recall the case with dirty read problem, right? So the dirty read problem, that is of much more importance for a database recovery manager, right? But nevertheless, it is the duty of the concurrency control manager to prevent dirty reads, right? So that was just an example to show you that concurrency control manager not only strives to achieve the isolation, but also uh, tries to help in the process of recovery, in the sense that it will not create schedules which are downright very hard for the database recovery manager to take care of, right? Because remember that in the schedule, whenever a transaction crashes, or it reaches and it fires an exception or something like that, it is the duty of the database recovery manager to sort of undo whatever right operations that particular transaction have done, right? So, they are not independent. That's all I want to say. And in this particular video, we are going to study schedules from the perspective of the database recovery. And then finally, when we go into the next chapter of concurrency control techniques, whatever protocols that I'm going to teach you in those videos, there I'm going to show you that how those protocols help in both achieving conflict serializability, and also they help in database recovery, right? So the protocols are designed in a way that they help both in concurrency and in recovery. Okay, so with that, let's get into here. Why recovery is needed? I think I don't have to cover this. A recovery is needed whenever there is a computer failure. Either your system can crash, your OS can crash, or downright your hard drive may itself get burned off or something like that, right? So that is a computer failure can happen, a transaction error can happen. For example, some kind of an exception can throw up, which will force undoing of a transaction in from the middle. And there can be some errors, right? Of course, uh, we have not talked about this, but even some concurrency control enforcers, so to say, there are some kind of concurrency control techniques which are sort of optimistic, in the sense that they let a transaction proceed, and when they realize that something is going to go bad in terms of conflict serializability or something like that, then they force a rollback of that transaction, right? So there are techniques like that. I don't know whether we'll get time to study them, but it's good to know that there are such techniques. That's why this is written. Concurrency control enforcement may also cause rollback and recovery. Okay? Some other things like disk failure, network failures, and all the list goes on. I think you yourself can guess what are the things. Okay, so given any failure, either from the system hardware perspective or software perspective or some concurrency control perspective, recovery needs to be done. And for recovery, the database system maintains a very systematic log, and in this log, basically it keeps track of all the transaction operations which have affected the values of the database items. And in fact, writing of this log and all that, there are very formal ways of doing it. I don't know whether we'll get time to cover all of that, But the thing to note is that this the system log is kept on the disk, and it is also periodically archived and all that, and your database system actively manages this log, right? And at the time of crash, this log, when your system recovers from the crash, this log is retrieved to check what needs to be fixed, so that your database system returns to an consistent state. Okay. And this system log, it basically notes what all operations a transaction has done. Whenever a transaction starts, it notes that, okay, transaction ti has started. Whenever a transaction writes a data item x, what was the old value of data item x, what was the new value of data item x, so this delta is stored in your system log. And depending on what is your recovery algorithm, the system also stores, if whenever a transaction t reads a data item x, it makes a note that this data item x was read, right? So all the read and write operations are written into the log. And then similarly, yeah, these two are quite special. Okay, let's see what these are. So commit statement, when a transaction writes commit to the system log, so it means that the transaction has completed successfully, and it's an affirmation that whatever changes it has made to the database, they can be sort of recorded permanently in your database, right? So it is some kind of an certification that a transaction has done everything that it was supposed to do, and there were no errors, no exceptions, nothing. And it's like this: when you are buying a ticket in from IRCTC, right? So just before issuing that ticket, right, you will commit your transaction, right? So reservation has been made, then you commit your transaction, right? So that is what is called as an commit point. So abort means that a transaction has aborted. So let's talk a little bit more about this commit. Okay. So when all the operations in a transaction, they have been executed successfully, and those updates have been recorded to the log, right? So I'm going to stress here this part, right? I say that the whatever operations this t did, read or write, as long as your log is up to date, your actual database may not yet be up to date, because there might be some pages which are still sitting in the main memory, which have not yet been flushed out to the secondary memory. So I will not say that your database has been updated in a very strict sense. Although I may have said before that if the database is updated, I'll say commit. But in a very strict sense, for the definition of the commit, I'll say that your log has been updated completely, right? And the log is written to the disk. After all of that has been done, then transaction T can claim commit, right? It can say that the transaction has committed. Okay, so there are actually very detailed protocols for this, right? So I will not go into the details of the protocols, but the thing that you should remember is that a transaction is allowed to commit even if just the log is up to date and the log is written to the secondary memory. The actual database may not yet been modified, but if the log is up to date and the log is in a uh, stable memory, that means secondary memory, then a transaction is allowed to commit. That is enough, right? uh, and why is that? Because depending on your the implementation of your database and all that, those pages, whenever you have to write anything, what you do, you don't go ahead into the secondary memory and write, right? No, the disk page is actually brought into the main memory. You make changes over there, and then the page is flushed out. You may recall this from your operating system. Okay, so that might still be happening. But if the log is up to date and log is written to the secondary memory, I'll say that my transaction is committed, and then I can give a green signal to my user that, buddy, your whatever changes you want to make, they have been made, right? The actual flushing to database and all that, that may happen later also. But the log is up to date, you can give a green signal. Okay. Now, in this case, when a system crash happens, what you will have to do is that you have to just examine the log, because we are always guaranteeing that log is up to date. Okay, now you will trace the log, and then you will see that, if a transaction has written commit in the log, you will have to redo those operations, because whatever changes the transaction made, those pages may still have been in the main memory when the crash happened, right? So you will have to redo the operations of the committed transaction, and then you will have to do undo of all the transactions for which there is no commit. Okay, so that is how the recovery manager works, right? It always ensures that log is up to date, and before giving a green signal to a user that your transaction has been committed, it ensures that the log is written to stable storage. Only then you give a green light to the to the user, right? Now in this case, whenever, as I said before, whenever a failure happens, you just have to take up the log, and then that if a transaction has written commit to the log, that means the user was given the green signal. All you need to do is that you need to just redo these operations, because some of these changes may not have happened to the database yet. And then for the transactions for whom there is no commit statement written in the log, you have to undo those operations, right? So this is a very high level of what your recovery algorithm does. Okay, I still took time to cover all of this, because I may not have time to cover actual recovery algorithms, right? Okay, so just a view of how recovery happens in database. Okay, well, I know I just told all of this to you, when to undo, when to redo, right? Okay, so this is what I was saying. Force writing of log. Before a transaction is committed or a green signal is given to the user that your ticket has been booked, any portion of the log that has not yet been written to disk must be written, right? This process is called as force writing of the log before committing. Okay, so this is a very important step. Okay, so now what we are going to do is we are going to study some schedules which can be generated due to some interleaving of transactions, and then we'll see those schedules. We'll study those schedules from the perspective of recoverability. Okay, uh, some schedules will be, they will be easy to recover. Some schedules will be downright wrong semantically. We'll see an example of each one of that. Okay, so the first case is what is called as an recoverable schedule. Okay, let's take an example. Achha, I don't have an example. Okay, so recoverable schedule is a schedule where no committed transaction needs to be rolled back. Okay, in other words, uh, you know, if a transaction is allowed to commit, then we are giving it a certification that you did everything right, your ticket is booked, and once that commit has been given to a transaction, it will never ever be rolled back under any circumstance, right? So a transaction where that is happening is called as an uh, you know non-recoverable schedule, right? So in other words, a schedule in which you will have to roll back a committed transaction is called as an non-recoverable schedule. right? So what's the opposite of that? A recoverable schedule. So if you want a formal definition, a schedule S is called as recoverable if no transaction T in S is allowed to commit until all the transactions T dash that have written a data item that T has consumed have committed, right? So let's take an example of what is a recoverable and what is a non-recoverable schedule. Okay, let's see this. Okay, so here what is happening is that T2 was consuming this right? Okay, and then similarly over here also this guy was consuming the output of T1, right? So it was dirty read. We'll talk about that later, but from our definition of recoverable schedule and non-recoverable schedule, if you evaluate this will be called as an recoverable schedule. Why? Because here in this transaction T2 is consuming something from T1, right? So T2 over here is consuming something from T1, and whenever it has done like this, T2 did not commit before T1. If this commit operation of T1 was somewhere down the line over here, then this schedule would have been a non-recoverable schedule. Why? Because T2 consumed something from an uncommitted transaction, and then it committed even before the transaction from even before the transaction which threw out the output which this guy consumed, right? So if this commit was over here and then this commit was here, then you are sort of allowing T2 to commit before T1 has committed. That is a non-recoverable schedule, because you are committing after you are committing before the transaction, uh, from before the transaction whose output you have consumed, right? You are committing before that guy. That is an example of a non-recoverable schedule. But here this T1 commits before T2, so this is an recoverable schedule. Whereas if this commit was over here, that means T1 T2 was allowed to commit before T1, then this would have been a non-recoverable schedule. Okay. Okay, we'll see more examples. Okay, let's go forward. Okay, so now next we'll cover about schedules which require cascading rollback. So let's see this. So over here, T10, it read something, and then wrote A, and then T11 read this output from T10 and then wrote something again on A, and then this T12 again read this guy, and then it started doing something, right? So now if T10 aborts, then these write operations are essentially invalidated, right? So therefore this T1 and T12, both of these transactions must be rolled back, because they consumed a data item from a transaction which was not yet committed, right? So this, as I said before, this is what is called as a dirty read operation, right? So this is this process where all these transactions are rolled back because they have read a data item from a uncommitted transaction. This cascading of rollbacks is bad, right? So they are not as I would not say that they are I would not say that cascading rollback is a blasphemy, quote unquote. But nevertheless, what they do is that they complicate your recovery process, right? So here, if you are allowing dirty read, all you have to do is that you have to keep rolling back. You have to keep a track of what all read operations happened, and then according to those read operations, you have to keep rolling back and all that, right? So cascade rollback is not a blasphemy. Non-recoverable schedules is a blasphemy, because you are rolling back a transaction after you have committed it. In other words, you were given a ticket and then later you are receiving an email that your ticket is invalid. That is blasphemy. So non-recoverable schedules are strict no, means they're just not okay. Cascading rollbacks, from a systems perspective, from a performance perspective, cascading rollbacks should be avoided, because it unnecessarily slows down things and it complicates the recovery process, right? So schedules where this kind of a dirty read operation is not going on is called as an cascade less schedule. Okay. uh, yeah, so a more formal definition is that a cascadeless schedule is a schedule where every transaction reads only the items that are written by committed transactions, right? So this part read is sort of key over here, because there is yet another class of schedules called as strict schedules, in which a transaction can neither read nor write. Okay, so there is a subtle difference here, right? So in cascadeless, and you are not every transaction reads only the items which are written by committed transaction, right? It cannot it cannot read any data item which has been written by uncommitted transactions. In strict schedule, you can neither read nor write, right? So this guy is sort of much more strict than cascadeless schedule, right? So the way to, in fact, all these three schedules, which I covered, they form an hierarchy. So at the top level, you have recoverable schedules. Okay. So first, let's say that, you have a set of all possible schedules. Some schedules in that set of all possible schedules will be recoverable schedules. And inside the set of recoverable schedules, some will be cascadeless schedules. And inside the set of cascadeless schedules, there will be some strict schedules, right? So that is the hierarchy which is formed across strict schedules and cascadeless and recoverable schedules. Okay. So you should remember that. So by that I mean that, a strict schedule by definition is cascadeless and recoverable, and a cascadeless schedule is by definition recoverable schedule. Okay, so let's see an example or two on this. Right. Okay, let's just see the schedule. So here transaction 1 has read an item X, then written an item X, then transaction T2 has consumed this X, but it was allowed to commit before. So schedule B is an example of non-recoverable schedule, right? So you can expect questions like this in your final exam also. I'll give you a schedule like this, and I'll ask you to classify them, whether it is recoverable, non-recoverable, and if it is recoverable, whether it's cascadeless or cascading, and then further, if it is cascadeless, then is it strict or not, right? So in that case, you have to closely see the definitions and then classify the schedule accordingly, right? So you can expect questions like that. Okay, so as in homework, I would want you to go through these schedules. So the terminology over here is that whenever I write R1X, I mean that transaction T1 has performed a read operation on data item X. Whenever I say W1X, I'll say that transaction T1 has performed a write operation on X, right? Things like that. When I say R2 or W2, I mean that transaction T2 has performed read. And over here, transaction T2 has performed write. So when I say A1, I mean that, transaction T1 has aborted. Similarly, you can guess what is C1 and C2. C1 means transaction T1 has committed, and C2 means transaction T2 has committed, right? So in this terminology, we'll use the same terminology in the exam also if I give this question, right? So you have to see the interleaving and then cross check with your definitions of recoverable schedule, cascadeless schedule, and strict schedule, and then classify these as appropriate. Okay. Yeah, sort of a closing slide here. So as I said before, that a database must provide a mechanism that ensures that these schedules which can get generated are both conflict serializable and recoverable, because this is a line which we do not want to cross, and preferably cascadeless. Okay, because cascading rollback is a mess. It takes time and unnecessarily loss of throughput and performance, right? So that is the goal of the concurrency control mechanism, right? So it ensures both conflict serializability and this, right? Of course, this is the now you can say that this is the legacy requirements. People have played with this a whole lot. They relax this to get some weak levels of serializability definitions, and they they have a whole lot of algorithms on that.